So no required text, but I will say that this particular book has a couple of examples of fitting to data, right? This is what we do as physicists. We have information, and then we fit a model to it. We compare observations, we compare measurements to model to theory. So today is sort of an important one. We're going to fit things. So fitting models, fitting mathematical descriptions to data, and like, how can I tell that I did a good job, right? Other than sort of, I think this looks right. There are some metrics that we can use that tells us whether or not we actually did right or which one's better. And so the important one is called chi-squared. You may have heard of chi-squared already. Yeah, okay, so this is one of them. We're going to do linear regression and minimize weighted residual. So this is sort of like, this is most fits are. And you go like, but I just have a line fit? And it's like, well, here's the fun part. If you do a line fit in log space, it's a power law. And in physics, if it's not linear, it's a power law. And sort of everything else is rare. So this will stand you in good stead most of the time. It's like, if you it's like, well, it's a power law. It's like, great, I'll just take a log of x and y and run from there. But like, what we, sorry, this is what I want to talk about today. This is what we're going to talk about later. This is the right one, okay. I want to reiterate what I said on Friday, and I want to have it on the record, so here it is recorded for this class. The presentation for the midterm, right? This is something for you to check on. So what should go in? The main conclusion of your visualization. What's the strength? What's the caveat? So conclusion, strength, caveat, context. I could have bold-faced those. I don't want to hear what the main conclusion is. If it's a good visualization, I can tell you, right? It's immediately obvious. But I want you to verbalize that, like to actually put it in as part of the presentation. Strengths and caveats should be their own slide, right? This is the strength, this is what I like arrows to the things that you like, and then maybe an arrow or two of the things that you go like, okay, that's a weakness. What's the context? This is the important one. Why was this graph even made? Why was this published? Why was this considered interesting to the public as a whole? And then, you know, to you, like, scale to new data. This is something that for astronomy and physics, and especially if you do machine learning, for example, like if you do big data, and somebody goes, oh, look how good this particular machine algorithm runs on this particular kind of data. You go like, great. When are we getting new data? And the answer is in 30 years when the next NASA probe launches. Then why am I here? Like, that's not important. But, or it's the kind of thing where I look at it and go like, that's great, but that's all the pulsars we know of, right? We're never going to get more data. You just classified what we have really well, but it doesn't scale to anything new. Or is there new data, but it's like, yeah, but that's going to be so gigantic that our tiny little model is not going to deal with it, right? So this is the kind of thing where it's like, does it scale up? And this is something that is also important for fits. And is it ethical to use? We sort of got derailed a little bit on Friday. I love getting derailed on a Friday. That's fine. I love the discussion. That was really good. Ethical to use is really what your take on that is. So your particular principles are your particular principles. If you are a college student or high school student, you are now thinking about what your principles are. Great. I am not here to tell you what they are. I'm just quite eager to hear what your application of those are, because you picked this visualization because you were interested in this, and then you had an opinion about that, and then that opinion might consider, you know, your ethics for this. Where you're gonna go, oh my gosh, this is absolutely not okay to do this. Or you could go, well, this is the way the world is. How do we deal with this as a society? This is my opinion, right? So if you want to have a slide on ethical, absolutely, like, well, that's bonus. So if you don't have one, that's perfectly fine. You go like, this is data, this is, you know, hard numbers, and I don't particularly care. So that's, you know, these two are bonus slides for you. Conclusion, literally the 30 seconds, 10 seconds, the, you know, elevator pitch. Should be the last section in the abstract. If you're looking at a whole paper, the best plot if the whole paper should support it. So like, that's your plot, right? This is the thing that gets supported by this. The conclusion is the thing that you This is the graph you show your aunt, go like, no, this is what the case is, right? This is your final argument. Strength, it's a new method, it's new data, it's sorely needed solution, it's a well-described use case, it's clearly laid out conclusion. What are the strengths of this visualization? It's like not just, it's important, but also, hey, this is instantly recognizable, or it is intuitive, or something like that, right? The weaknesses, poorly or hand-waving rationale, or things like missing or misrepresented data. Like in a graph, this would be the cardinal sin, right? This is the worst one. Inappropriate or poorly motivated methodology. Like, I don't want to turn this class into like, look how bad this graph is class, but I've seen plenty. But it is the kind of thing, for example, where you have enormous error bars and somebody's fitting a plot through, and you go like, I could have drawn any line through here, and I couldn't, tell you which one was preferred. So logical misses, for example, like how do you get from A to B, or obfuscating, like you're actually actively trying to hide something. This is a very attractive thing to do. Like, I found the worst plot in the world, but the thing is, you're standing up here and you're sort of defending, and at that point you've given yourself the worst ammunition, because you've given yourself the worst plot in the world to do this. So unless you have a real issue with it, or go like, this is what I want to address, I would say the weaknesses are more of a, this is what I can't read, this is where it gets, it's good for this kind of audience. So missing the audience, for example, is a fantastic weakness to assess. Like, I got a good plot, and it's a great plot in a scientific paper, but you published it in the New York Times, and nobody can read it. Nobody gets what this is about. So that's the kind of weaknesses that you should probably go for, but this is the kind of thing that is right? Context is everything. Like, why is this your plot? Why is this interesting? Why is this important? So I want you to very explicitly say context, the why. We did the how just now, and the what, like what is it trying to say, but the why is an important one. Is it well illustrated? So really, is this good color of colors or shapes? Is the caption, like, is it placed in context? That is such clear labeling that the caption is just extra, right? Those are chef's kiss kind of visualizations, right? I don't have to read anything in the small print below, because I don't like small print. I need to get my glasses, that kind of deal. So if it's really well captioned and I can just read everything, fantastic. Are you convinced? This is something that comes from you again. Like, we go like, hey, this was, actually, this made me change my mind about this, right? Or like, actually, this helped me refine my opinion. So scales to new data is really like, did all the data available, is this all there is? Is more data coming? Like, if you have, CDC data, it's like, well, the CDC isn't, stopping as of today, as of yesterday. So they're going to get new data. Like, will that be added? Can I think of a plot that's like this 4 years down the road, but it has new data in it? And would that be useful? Like, yes, in the case of CDC data, absolutely. In the case of, well, the next NASA probe is 30 years away, not so much. Okay, ethical to use, just, is this a thing that you should be doing? Okay, so that was the things that I wanted to make sure of, but you can also go look at these, right? So know the audience. So this is the wrong audience. This like appeared in Popular Mechanics, and it's about quantum mechanics, and it doesn't explain any of the labels, and who knows what a Hamiltonian is anyway. Why is this in Popular Mechanics, right? So completely missed the audience. Is it well adapted to the situation, for example? This is like, hey, this is a social media post, and it never loads. That's a problem. This is scientific, so usually the failure mode of Qt, right? You're trying a little too much. So good example, 3D plots in scientific literature that you could manipulate. Now, this sounded fantastic, right? This is like, you can make a 3D plot, and there's sliders, so you can actually present a three-dimensional thing and manipulate it while it's in the PDF. It crashed everybody's PDF viewer, so nobody got to see your paper. So it's trying a little. So that's like, is it well adapted to the situation? It's like, no, nobody's PDF reader can deal with this thing, right? So that would be an example. To be precise, include all the information. Like, do I have everything I need? Is there, for example, just an absolute terrible use of color? That's a perfectly valid thing to look at for weaknesses. And is it a little bit overloaded? This is quite personal. Some people who are, people are very comfortable working in a coffee shop with like people talking and lots of, background noise. People like that. There are people who cannot concentrate unless it's dead quiet or they have their noise canceling headphones on, right? So, and these people usually live together in the same apartment, right? So this is the kind of thing where it's like, is overloading a figure is a personal thing. Okay, so color wheel. Why did I bring back the color wheel? So that was about the presentation. Like, I didn't put in a transition slide, but that was in for the presentation on your pick of visualization. I need yours today. Excellent. All right. That's as much shaming as I do in class. So in high school, and I'm not going to start now. So why did I put the color wheel up here again? Because we were talking about complementary colors. And so if you're doing a data visualization and you have a fit to your data, you want to plot that, right? You want to convince your audience that your plot is good. And so actually having complementary colors to, for example, data and model, or typically like this is our you pick the color you like the least. Like, that's our rival group's result. That's our result, and this is our model, right? So people can actually separate the three out well enough. Like, you want to separate them out in the depth. You get depth from color. Like, having three colors like that are very complementary, so on either end of the color wheel, adds depth to a plot, which means that if you're being really mean, you make your rivals' points, light gray, and so they're all the way at the back, and then you plot your stuff on top. So there's ways to sort of put everything in perspective and sort of like in a 3D part of the plot. Like, your eyes put certain things in prominence versus the rest. Flowers use this to attract bees because like you're sort of away from green, so you stand out to the green background. Tetradic is a four-way, so as complementary as possible, right? You want to use those colors if you have one model and three kinds of data sets, for example. Like, that way people can tell them apart, even if they're on top of each other. And so this is the kind of stuff that you only use for the data, not for models. I was trying to tell this to a colleague because he was using, one color like this for three different models. I'm like, I can't tell them apart. Like, I understand that there are three models, they're all sort of the same, but I can't tell A from B. So, maybe use something more like this. So we have the XY plot, and the XY plot is our model fit check, right? This is the fit check. I almost called this whole thing fit check, but I realize I'm too old for fit check. So not this part. You have a line, you have points. And so how do you tell if this line versus this line versus this line is the better description of this data? Or if a circle is the better description of that data, right? So you need something other than a visual, but you can do this visually, and you can do this with chi-squared. So if you model something, a line through your data points, you have a couple of problems. You can under or overfit. You can under or over describe the data. If you have a linear description and it's not a linear relation, then you've underfit the data. You've under described it. If I'm using an 8-degree polynomial for something that's just a linear relation, I've overfit it, right? So what do I pick? So check against outlier-driven results. So think like, hey, if I'm doing a line and there's, I've got 5 points and the 6 points is like all the way out there, then, the whole thing gets skewed. Secondary effects, reasonableness of extrapolation or prediction. This is one of the tricks to go check if your fit's okay. If I just extrapolate this a little further, is that fine? Secondary effects are like, hey, is it not just linear? Is there actually a second thing happening, or is it just, an outlier that will have regression to the mean? Who's heard of that term, right? It's like we'll revert to the mean, regression to the mean. You get one outlier, and people are like, oh, Like, well, it could be one outlier, and then we go right back to, you know, the trend. So curve fitting things, this is, again, from XKCD, but, you know, it's inspired by XKCD. But I do kind of like the fact that you have linear, quadratic, logarithmic, exponential, log is a smoothing, linear with no slope. Sigmoid is also a smooth, if I remember. This is just a confidence interval, so it's really just a sliding scale where you take the average and the standard deviation. And piecewise is 2 models for 2 parts of the data, which, you know, there. This is, you can do that. This is literally a polynomial degrees of freedom to go through every point, which is way overfitting, right? Like that's, I can't just, like, same thing here. Like I'm already overfitting here. Because if I do this relation, where's my next point, right? Where is the next point? The next point's down here. That's not what you expect on based on the trend. If you expect on this trend, you kind of like, next point is here somewhere. If it's down here, well, this was underfit then. If this is a reasonable description, so how do I know that's a reasonable description? I need to know the uncertainty on my data. None of these points have uncertainty. Notice that? No uncertainty has been reported. Sometimes you don't get uncertainties. There was simply no measurement of that. Or you look at the owner's manual of the lab device and you go, well, they're clearly lying, because you should be able to get an idea of the spread around your model. That should be your uncertainty. So, physics of parameter estimation, like what kind of model do I pick? Logarithmic, exponential, mathematically they're sort of the same, right? So what do I go with? Well, there is hopefully some theory knocking about, and otherwise it's up to you. So here's the thing, like we like to measure things. Sometimes the things that we want to measure are directly measurable, like this length of this room, right? I can pick whatever I want to do the measurement of this room. I can pace it out. That's super uncertain. I can take a laser measurement and bounce it off. That gets it down to a nanometer, and anything in between, right? So I can measure the length of the room directly, yeah? But sometimes, the other times, the measurements are not direct, but come from a model. This process called inference, right? I'm trying to gauge if any of you have had some of these terms already or just had them floating around in another class. Okay. And for some reason, I'm out of the thing. All right. So we can either measure something directly or model 2 measurements. And so, for example, you have a scatter plot with some points that show your measurements. Practical example, time in seconds and distance in meters. This is time in seconds and distance in meters. So I'm running, and I'm basically, there's measuring. It was like I just got it. I've just marked off on the pavement, you know, every yard or meter. It's like, and so I've got 25 meters, and this is just me running, just to see how well I do. And it's like, and I'm just taking, you know, you take flash pictures, and that's like you can just measure where somebody's nose is at any given point. This is how people measured how fast horses were, for example. So you have these different points. These are all individual measurements of person at a given point in time as a function of, you know, this is the position as a function of time. I don't quite start at the starting mark. I actually sauntered a little forward, so I'm actually starting at the 5-meter mark, close to. Okay, in this case, the data seems to suggest that a simple model, a straight line, would fit your data. That's a good description of the data. That seems to be working. I mean, there's a flag a bit here, but that's it. To fit the data means that we'd be able to draw a line that goes through all the data reasonably well and allows you to predict what happens next. So like if I keep running, I'm going to end up at 30 meters at, you know, about 11 seconds, right? Linear regression is quite easy. You kind of draw the line, you go like, yep, that describes the model, okay. So how would you do that by eye? You kind of go, well, going through all the points is not, you know, it hits every point, but it's good in the middle. Like the distance between the points in the model is minimized. Yes, that is the key thing. That's what your eye is already doing. For this simple case, you would draw a line through all the points, and you can find, for example, the slope and the intercept. So here's the intercept, and we have the slope. The slope and the intercept are not measured directly. We are inferring them from all the points combined, right? These are the parameters of your model. So if you do a model fit like this, you kind of go, you already know a few things. Because you visualize it, right? You know a few things. One, the intercept doesn't go through 0. I can draw this line, it goes like, yeah, it's 4 and a bit. So you already know that if you have to give a hint, it's like, yeah, it's not 0, it's, you know, somewhere between 4 and 5. And if you go like, well, the velocity, the slope is positive. If I increase this one, that one increases. So I can ignore all negative values, for example. So you know something about your model already. In real life, data have uncertainties that are associated with them. If they don't, you can probably find out later, basically between the model and your fit. But there are ways to do it without. We'll get to those. But in real life, usually every piece of equipment comes with a, well, in ideal standardized environment, the performance of our thermometer is this, is within this, right? The standard deviation as we've measured it, as we calibrate these things, is this. You are bombarded with a measurement like that, right? Gas mileage for cars in commercials. Do you notice like the tiny little font at the bottom, right? This was done on a dry track with a professional driver under ideal like that's when you get the mileage that we tell you in our ad, right? Because there is an uncertainty to it. So if possible, they would put a error bar on that, but then they confuse your audience. So the good thing to do is to take those into account, those uncertainties into account when we fit the models to data. If they're all the same, then each point is equally valuable. But if we have like a crummy piece of data and a much better measurement later, because we learned how to do the measurement or whatever. And so inverse error weighting means that you weigh the points more if they have smaller errors. Often you get models, you fit a model through a whole bunch of points that come from different kinds of measurements. So imagine, again, the length of this room. I have the person who's measuring the length of this room with a laser. I have the person who's pacing it. There are 15 people who are pacing it out. And I have 3 people with a measuring tape. So these are different size samples. Like I have 15, 3, and 1 person with like the super accurate one, and like 3 that have a pretty good one, and then 15 that have like a like within the yard, I guess. And so what do you then do? If you want to get the average that works, you use the inverse error weighting. Like you give everybody an error. The pacer one's like within a yard. The measuring tape, well, it's long enough, so like within, I don't know, 1/4 of an inch, and the laser within a picometer, right? So now you can weigh everything accordingly. Weighing the errors will lead to a different result. Because if I just took the average, if I took the average of all of them, I'm weighing those 15 much stronger than the 1 person with the really high accuracy. See how that works? A little bit of a nod. Yeah, okay. Fantastic. So, for example, here is, again, the plot that we had earlier, but now I've given them error bars, right? And so if you do this measurement where you take, you sort of do flash photography as you follow somebody and just sort of go like, okay, well, they're here. Well, some of the time, they might be like this. Where exactly are they on the measuring leg? So that might actually be a little bit of a bigger error bar. And then some of them are, they're doing this. So you're like, yeah, they're exactly there. So I actually have more and less uncertainty by every measurement. Thank you for letting me mime that stuff because, so what I have here is a mixed data set, right? Mixed uncertainties for each piece of data. This is typical. This is not the standard. In lots of physics textbooks, the thing that I see is all the uncertainties are the same size. In all the examples with matplotlib, all the uncertainties are the same size. And then you all open up your first scientific paper and go like, why are all the uncertainties all over the place? Like, that point is this big, and that point is tiny, and like, why is everything different? Like, how do you even fit a line through that? So, well, you take the inverse, like, that actually gives you the confidence interval for each measurement point. And so if you do that, and you weigh, like, these are weighed lower than these, So you notice that the fit with errors actually goes through that point because it's weighed more heavily than this guy, because it also gives you, visually, you can sort of think of like, you're still allowed to wiggle this one and this one, because they're just, they're in the air somewhere. They're not sloppier, they're not less valuable or anything like that. The uncertainty is just a little higher. So, the best thing I know is like, it's in here. You can even have uncertainties that are going up more than down. So you can have asymmetric uncertainties. Okay, I'm running ahead of myself, but that is definitely also a thing. So you measure, your model actually changes if you take the errors into account. Another way to think about that is that you are taking more information into your model. The red line uses the x and y axes. The green line uses the x, y position, and the uncertainty to inform the model. So which one's better? I know it's Monday morning and I'm talking fast, but which one of these models would you trust more? The ones with lines on it? No, okay. The green one. The green one includes the error bars, right? It actually includes more of the information of what we know about our data. Okay. The green line is a better fit to the data because it takes into account the experimental uncertainties, right? The model is improved by taking the experiment's certainties, the confidence intervals, into account. So a straight line with using Python, using algorithms that do this stuff in the background. So it's fantastic. You want to fit a line through our cells, finding the parameters slope and intercept. So instead of doing, this is going to be the example for this week and next, there is something called lin squared, like that does just take linear square root, so it fits through the points that you give it. But if you want to do this, how would I go about that? I would have to try this a whole bunch of times. I have to try a bunch of different values for slope and a bunch of different values for intercept, just to see which one works best. And I need to have a definition what best means here, right? Not just visually go like squint at every possible option. So we can make a grid of all the possible values. Possible, doing a lot of work here. So each slope and intercept, like we actually give it a bunch of different slopes and intercepts. But that means that we have to pick which range we do. That's a decision we make. Okay? And everybody has a unique straight line. The straight line that minimizes the difference, so minimizes the difference between model and data, while inverse weighting the errors is the winning model. That's the best fit. So we'll go through all the possible combinations of slope and intercept pairs and find the one that minimizes the difference. So closest to all the points, weighted by the uncertainties, and go through every possible slope and intercept. How many different numbers are there in the universe? Well, I'm going to go from minus infinity to plus infinity for slope and minus infinity plus infinity for intercept. Or do I do something slightly more intelligent and go, wait, I know that this was positive and I know the slope was positive. Well, that's already half infinity now. So we've seen that fitting parameters can also be achieved by finding the model that is the closest fit to the data. This is coded as minimizing the function, loss function or error function. So you have n data points. How should we write that function? Chi-squared is something, data minus model for all the parameters squared, so that's the absolute difference, divided by the error, so inverse weighted, the error squared, and then sum them all together. Or like this. I have the function that I'm trying to describe, so give it the x values. I'm subtracting that, or subtract the y points from that, take the square of that, divide by the uncertainty in the measurement, and sum them all together, and that's called the chi-squared. So if I'm trying to do that here, here's my model. That's f of x. X is, these lines here. I am now, so the difference here is 4, so that's 4 squared, 16, plus minus 2 squared, so that's 4, so it's 20, plus 1, plus 1. So it's 22. Okay, 22, none of them have error bars, so I don't have uncertainties on them, so sigma is just 1. And so the chi-squared of this fit is 22. If I now do, I don't know, a straight line. Let's go with this straight line. I can do this is the kind of math I can do in my head. So, okay, here's a straight line, this straight line. Okay, I've got 2 squared, that's 4. I got 3 squared, that's 9. I got 1 squared, so that's 1. So that's 10. And then 2 squared, which is 4, so 14. This is a better description of the data, this line, than this blue line. It's better. Now, there might be a best option. Also, there might be other points, right? But this is how you compute it. OK, so I take a slope, and all the possible slopes I was thinking of, and all the possible intercepts I was thinking of. Now, notice that I went from 0 to 35 because that was sort of the range of my y-axis. And I did the slopes because that's I need to be positive. It's more than 1. So I sort of guessed the slopes. But this is a decision that you make. Like if you do a chi-square fit like this and you run through a bunch of slopes and you run through a bunch of intercepts, you have to guess the range over which you're fitting. That is something you have to do beforehand. That's a decision you make. And then you have to say, well, what step size, right? Do I do tiny little steps or do I do huge steps? And so if I do tiny steps, I get a much more accurate result, right? I can actually get it down to a couple of decimal points. If I don't do that, I only have to do a few computations. So it's a really kind of a how many models. Now, initially, when we were doing punch cards and stuff, this was a valid concern. It's still a concern because you, instead of fitting to like 10 points, you're fitting to 1,000,000 points. And every fit just takes your computer a moment to compute chi-squared. So there's always a point where you sort of go like, OK, that's too much detail. But you have to decide the range and the step for a chi-square fit like this. Now, what am I plotting here? This is the chi-square landscape. So here is like the same chi-squared for this combination of intercepts and slopes. 6,000, 5,400, 4,800, 4,200. Oh, it's going down. So if you think of that as a 3-dimensional model, it's literally you're going down to the lower chi-squared. We will re-encounter this when we do Carlo-Markov chains, which is sort of right at the end of this class, right? So so if you compute this whole box worth of values, you get a like, oh, here's 4,800 going down, 3,600, 3,600. Oh, it's like, suppose we're here, we're going like, we're going back up. Oh, go back, go back, go back, go back. It's somewhere here. And if you go here, they're like, oh, it's going down, still down. And so somewhere, the best option is somewhere in this little ellipse here. So a lot of fit programs are essentially sort of jumping through this space and kind of going like, I'm here. OK, I'm going to just randomly walk over here. It's like, it's still high, still high, still high. Oh, it's going like, oh, it's going down. It's going down. I'm going to follow the gradient. And then up too far, and you walk back, and you just eventually sort of bounce around. And as soon as your gradients get steeper, you start taking smaller steps, and then you end up as like, ding, 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 ding. Oh, here it is. This is where the optimal value is. So instead of computing all the entire box of values, sort of randomly jump through. Yeah, that's what Monte Carlo Markov chain actually is. But so foreshadowing, as this is called. But so we have different kind of optimizers that sort of jump through the chi-square landscape, but failing that, you just brute force it and you calculate the whole thing. But then you have to figure out what kind of ranges. So what sort of relation do I fit? I said linear. Well, maybe there's a theoretical model. That sort of gives you the mathematical expression that you should fit. An estimate based on data visualization. That looks like a line to me. That looks a little exponential. That looks like a... Otherwise, we guess. We try a few options, right? Oh, like let's have a look. And start with the simplest polynomial. Like if nothing else fails, a polynomial will describe it. If you go, there are so many different things going into it. It's a slowly changing thing. Then yeah, I'll go with a polynomial and just add complexity as you go until the chi-squared is better. Like you will always get better chi-squared with the same data, but it's like reduced chi-squared is the chi-squared divided by the number of free parameters. And what do I mean with free parameters? Intercept and slope are the two model parameters. So I do chi-squared here, I do 6,000 divided by 2. That's 3,000. If I then want to compare that to a model that has 3 parameters, I need to divide that one by 3 in order to get, like, do I actually get closer? So that's the reduced chi-squared. You can model everything with a polynomial. It's just a question of whether or not you should. And if you have enough data, and you have enough parameters, you can literally fit all of this. Here's a photo. Lots of people have tried to do a polynomial that fits the stock market. Because, oh my gosh, I can then predict the stock market. But you need so many higher order parts of the polynomial to do that that it essentially becomes meaningless. So not so far. Although the machine learning people are now going like, oh no, we can. All right, under and overfit. Here's a bunch of points. Here's a line through it, right? Let's just fit a line through it. This is the best line fit through it. There's a bunch underneath. There's a bunch over there. It's like, yeah, it goes through. House size and price. One degree of freedom because, you know, I'm just forcing it to go to 0, for example. So D1 is a polynomial of the first order, which is literally linear polynomial. Yeah. D2 is like, now we have an x squared component to it, right? So it turns over. This seems like a better fit to the data, just visually, right? And then D6, this is overfitting. I'm basically trying to hit every point here. Now, visually, this again, it's overdone, right? It's done too much. But you can kind of go like, well, house size and price, you know, one of these two, you know, if you just had to guess without the visualization just yet, you go like, well, either one of them I can totally see, although maybe, you know, the price goes wonky beyond a certain, you know, if you have a one-family house, what happens if I add 5 more rooms? I'm like, I don't know, like, does the price even go up? So maybe, you know, you get something like this. So how do I tell the difference between these? Well, A is get one more data point, right? So find a point here, like does that end up here, or is that closer to here? Like that way I can tell the difference between these two, right? Get new data. Like how do I tell if I'm doing under overfit? Step 1, get extra data. That's honestly, if there's a knee-jerk reaction among physicists and astronomers to go like, which one of these two models, they'll go like, get more points. You can always kill it with more points. Like you can always settle the thing with more data. That works. The second thing is to do the reduced chi-squared, right? So this is 1 degree of freedom because I fixed it here. So it's chi-squared divided by 1. And here it's the chi-squared divided by 2. And is that reduced chi-squared or better? Is this a better description? Another thing that you can do is simply do the fit but remove a couple of points and see if the fit is still the same. And then if the chi-squared, so you split your sample. You can do 50-50, you can do 20-80, something like that. You fit everything with the big sample, and then you go like, all right, and now I'm grabbing my remaining 20% and see if the chi-squared for the test sample is the same as it was for my model sample. See how that works? It's go out and get more data, but you know, you're going, I don't want to get more data. I'm just going to split it, model with one, and test with the other half. Half, 20%, 30%. Because if I do that here, and I leave these two out, for example, my model is now suddenly going to be like, you know, whoop, goes that way instead of this way or whatever. And I'm now adding these 2 points, and it doesn't go through those at all. I'm like, okay, I'm overfitting here. So if the chi-squared for a test, a model/test sample is the same for both, you know, the model and the test sample, like they're on the same order, right? They don't have to be exactly the same, but it's like, okay, this different, this the same, this no, it's overfit. So you can tell where when you're overfitting versus underfitting. This, especially if you don't have a theorist helpfully giving you a, like, this is what the mathematical model should look like, here's your 3 variables, you know, if you don't know how many variables you have, you essentially are trying to model something new, or worse, you're just trying to get rid of the trend here, then yeah, knowing what the actual shape is and how much order the polynomial has is how to do it. And so getting a good chi-squared and actually deciding underfit or overfit, that's important. So the reduced chi-squared is the chi-squared divided by the number of degrees of freedom. The degrees of freedom, the number of parameters in your model. So you've got reduced chi-squared, or sometimes it's between these pointy brackets. What also works is just simply extrapolating and see if the model gets silly at some point. Because that tells you over the range over where this model is valid. For example, Newtonian gravity is still perfectly valid, right? It's perfectly valid unless you get too close to a really big gravitational mass. So that's the range of applicability. Like Newtonian gravity works just fine for the vast majority of the solar system. Venus and outwards just works fine. So you don't have to put in GR anywhere. But if you get to Mercury, then yes, the precession of Mercury needs GR, right? So that's where you get to the point, like, or your precision is to, within a few centimeters, then yes, suddenly you need GR. Like either your requirement is higher or, so it tells you what range your model is reasonable for. And extrapolating, I find that incredibly useful, right? You can just go, and that's where we heat, time, for example. Like, time is a fantastic one. It's like, okay, do we have enough time to do this? So if we look at the very first galaxies, James Webb is looking at what we think are very early galaxies. So stuff that just formed and the light start traveling towards us. So 13 and a bit billion years ago, which means that you have a few 100 million years to make that thing between the Big Bang and what you're looking at. So does the universe have enough time to make stars and then also make the stars that we look like? So is my model enough to do that? Like, I have hard constraints. If my model says I need a gig a year to make something, like a billion years to make something that looks like that, and I have 300 million years to do it, it's not going to work, right? So time is usually a good constraint. Things like, I love this one. For fun, had a target and I put it in the time estimation tool, like how long would I have to look at it with this particular telescope? And it came up with a exposure time that was longer than the universe has been in existence. So it's like, oh, well, we're definitely not doing that, right? That's a hard limit on experiments like the Hubble time. So extrapolating into absurdum is XKCD's specialty, but I would also say that it's a very useful thing to occasionally do. For example, the James Webb Space Telescope. And I left this in because the last time I taught this, it was still getting ready for launch. And so, it was the now 2021. And it's like, well, if I do a linear fit to the launch date that NASA has announced, and I just keep going, and this is the linear progression of time, then this is where they intersect, right? This is a data, that's a model. We've assumed it's linear. And then there's like, okay, well, this is the intercept. So we actually beat the intercept by, it was launched in December 2021. This is a kind of plot that I quite like because it shows, space is hard. And so you get delays. And so here is, 0.0 is the first launch date that you announce. And you hope you're going to get the first launch dates, but this is when you're bolting the thing together and somebody's procuring still a rocket for it and all that stuff. So you're still 80 months out, right? And they're like, well, linear progression of time, and there's the first delay because it turns out we can't get you the launch vehicle in time. And here's a second delay because it turns out that, so-and-so that needs to be fixed. Or we found a bolt on the floor, where did this come from? That kind of thing. And so, but what you notice is that, yes, the delays become more frequent, but they become smaller. So you're actually progressively getting closer and closer to your launch date anyway. This is what a complex program actually looks like. So there's absolutely no reason to fit a line through that. Right? Why was that our model? And it only works because we made the plot big enough and the points small enough that that looked like reasonable scatter, but there's basically scatter of about a year there. Okay, so this is not the point where you switch off your brain. I have a good description of the data. Doesn't mean that you go, and we're done, right? I will be booking my flight to Stockholm to receive my Nobel Prize, please and thank you, right? This is not where you stop thinking. You now have a good description of the data. Now, is the part where you just tell everybody, why is this a good description of the data? Like, how is this a model that works for you? So the fit test is if you have a reasonable data set size, you split it into fit and test subsamples randomly, typically 80-20, but 60-40, pick it. Redo the fit with just the fit subsample, compare the fit and test sample chi-squared. Do they equally well describe your data? These should be comparable, otherwise it's an overfit, right? If the fit sample is really low and the test sample is really high, then you've overfit your model. If the fit and test sample are similar, then we're about good. If the fit sample is really high and the test sample is really high, I'm trying to think if we can actually underfit with this as well, but it's mostly a test against overfit. Machine learning, we call this the test train or the test train and validation samples. Like there's actually three different, you split it in 3 ways. So you do this train, you test it, you train, you test, you train, you test, and then when you're done with that whole loop of training and testing, you're going to like, okay, this is the right set of parameters. Then you actually have a third subsample, we use that for testing. So the visual sanity check, and this is like one of those, when I was a grad student, one of my professors, sort of showed this, and it's like, oh, what a trick, right? So this is very much of the paper beats rock kind of things, where instead of doing that whole neat chi-square check, you just go, do I still believe the fit? 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 I just block out a third of the plot, and if I'm now going, I don't see it, then you've got a problem. That's sort of like the cheap way to do that. That's also when you sort of trust your own instincts with the fit. And I would actually do, this is a very good first check. To just do this whole like, okay, yeah, now I don't believe the fit anymore. It turns out this one point was sort of driving my whole conviction that this was true. That typically is what happens. So we had data visualizations. We did all the do's and don'ts of that. We talked about what I expect from you for the midterm. I have all your data visualizations. Please get me the presentation slides by Wednesday class time, preferably a little bit before so I can see if it actually runs on my computer. Now, I said we're doing this exactly like we do a scientific meeting, right? And so it is not coming Wednesday, the Wednesday after spring break. Yeah, I saw some eyes pop up and I was like, oh, yeah, okay. No, it's not coming Wednesday, the Wednesday after. Coming Wednesday, you can just work on assignment 7 here. But for next Wednesday, we're going to do the midterm. Please send me the slides, essentially by Tuesday evening so that I, in the morning, can check if the thing runs on the computer. This is very much how you do it with an actual scientific meeting. There's like one person's laptop sitting there, and you're like, oh, I'll just connect up my laptop. Like, no, because we've all just sat there and just waited for the laptop to finally start talking to the. No. Keep it moving. Keep it moving. You've all got 15 minutes. So they're all on here. There's basically an organizer who keeps everybody to time. Usually it's very friendly. They go like, I'll give you a 3-minute warning. I'll give you a 1-minute warning. And then there's the less friendly where they go stand next to you and go like, yes, it's time to wrap up. And they're all very friendly and collegial. And at some point, somebody just picks you up and moves you off stage, right? Because, you're way over. So I won't be like that, but we're trying to time it as well. Other people's time is valuable, so you've got to get your point across in the 10 minutes plus 5 minutes for questions. So 10, 12 minutes is what your presentation should be. You've got a slide for the why, the what, the how, pro, con, and then if you want to do a couple or more things, that's fine. But make your slides, and then we sort of evaluate how everybody did later, what was good, what was bad, what you could work on. This is the easiest possible classroom. This is the lowest threshold, right? This is why we do it in class. I had tons of grad classes that had a presentation component. Here's a paper, go tell us what it's about. because it taught you how to do that, right? This is a valuable skill, whether or not you're a scientist, whether you're a data scientist, you go in industry, you go in academia, you're going to have to communicate what you found. If you're a quant at Google, you're going to have to tell your team what you did, what you found out, and this is how you do it. So that's how it works. So please have the PDF, PowerPoint, Outlook, whatever you want to use. LaTeX, I've had people use LaTeX. I don't know why, but okay. Makes a PDF, fine. There's slide transitions. You get to use this. We flip back and forth, etc. And I'll time you, and I'll have notes. And that's the midterm for next week, Wednesday. Yeah? All good? Fantastic. Thank you so much. I'll stop the recording here.
Yes, that is a very important clarification.
Yes, I realize that. Stop. Are we stopping? This thing is just... Ooh, I can see my own bad hair day here.